Okay, class, welcome to lesson 1 for chapter 3. This is a chapter all about exponents, exponent laws, exponential relationships. We're going to look at exponential growth in the first section. I have, just for the introduction, just a couple pictures here that will show you some patterns in nature, which we will explore with the pine cone, and we'll look at some of the Fibonacci-like or exponential-like patterns in this pine cone. We have seen the Fibonacci sequence before in sequences in series, if we've come through chapter 6 at this point. And now we'll find that some of the patterns that are found in nature exhibit the Fibonacci numbers. The Fibonacci sequence is that well-known sequence which is recursive. It starts out 1, 1, 2, and then we add the previous two numbers, so we get 3, 5, 8. So those numbers are found quite often in different places in nature. Taking you to some of this in class, we'll have a chance to explore a website which shows maybe the reason why things grow with certain patterns in their petals or their cones. And the chapter problem for this chapter is all about natural phenomenon and things that we can observe in the universe. So you have a chance to apply exponential functions and exponential relations to things in our real world. The prerequisite skills is an area where we might just want to spend a little bit of time as we start out chapter 3. The first section is mostly about patterns that exhibit exponential growth. However, when we get into exponent laws, we'll have to go back and look at product quotient power of a power rule. So for now, in class, at this point, you've probably carried out the simulation of an animal population as it grows and had different breeding pairs that were either mature or they were breeding. And in this case, there was a pattern which we looked at in class, and out of this came a Fibonacci sequence in a lot of different areas. We looked at total number of pairs, number of non-breeding or maturing pairs, number of breeding pairs, and then breeding pairs that had just for the first time been bred. Keep in mind, all the symbols in this diagram represent two animals, a male and a female pair, and this is not extremely accurate, but as it was mentioned, the 1 month period of gestation and the 1 month period of maturation is pretty close to the rodent family. So out of this, we might want to look at, just to review the data that came out of that. We'll just sort of examine the total number of pairs and just see that this is very close to exponential. So examining total number of breeding pairs, just counting all the symbols of different types at each level from time 0 to time 7 months. At the beginning of the 7th month, there have been 21 pairs at that level, assuming no mortality in our population. So this is exactly the Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, 21. When we go and graph this, we can go in here and set up our stat plot. We'll turn it on and scatter plot using list 1 and list 2, and I'll use zoom 9 to create a quick scatter plot of that. So there's our graph. Now it looks very much like an exponential curve, and it's very close. If we were to try to fit a curve to this, we could go in stat calculate and choose something that would resemble exponential. So we can go down here and choose exponential. Having selected the regression, option 0 here, we can go in, and this calculation's previously been performed here. I want to paste this into Y1, so I'm going to pull up the list that create this scatter plot, 1 and 2. I'm going to go to the variables menu, Y variables, choose function Y1, and there we get our equation again. So it's in the form A times B to the exponent x. So this is what we call the simplest exponential function. Our multiplier A, our base or a growth rate B. This would tell us that this population is growing at a rate of about 60% each generation. So from month to month, there's about an increase of 60%, and our correlation coefficient here is very close to 1, so it's a strong fit. Now when we go and look at the equation. There it is. We look at the graph. There's our scatter plot, and overlaid on top of that would be our best fit curve. Now, with the Fibonacci sequence, if we were to go back to our data, we could take the numbers in the Fibonacci sequence 1 to 21, and if we were to take ratios of those, we would find that there's something called the golden ratio, that the ratio of these numbers gets closer and closer to the golden ratio, which you may have studied before in math or have seen it somewhere else. And the ratio here is 1.5, and then this becomes 1.6, and then this gets closer to 1.7, 1 2/3, and it actually oscillates back and forth between a little bit above and a little bit below the golden ratio, which is not quite 1.6, but that's what we saw in our regression curve. That was our multiplier was very close to 1.6. So the Fibonacci sequence for a situation like this is quite close to perfectly exponential. Okay, now out of this, we just want to maybe summarize some of the properties of an exponential growth system. So here I've just shown sort of a simple exponential relation. The function y equals 2 to the x. The graph is a little bit unclear here, but we have our y-axis and our x-axis. A couple things that distinguish this from other nonlinear types of relations. It's nonlinear for sure, and the growth is demonstrated as an increase at an increasing rate, which means that the function is rising, and it's rising faster and faster. Okay, so when you take 60% of 21, for example, you'll increase more than if you took 60% of 5. So that's what contributes to the rapid increase. The simplest type of exponential growth is a function in this form y equals ca to the x. I might want to modify that here now that I've seen the graph and calculator. It reminds me that we often use b for the base and a for the multiplier, and it's similar to the coefficient that we've used in a quadratic function or quadratic model. Okay, so there's our property for the algebraic form. We have the dependent variable value increases by a constant factor. That would be the b value. I have to just modify this as well, that if we're going to call the base b, we also have to say that b is greater than 1. Okay, so we can control exponential decay using a b value that's less than 1. We don't need to use a negative base. This hasn't been demonstrated yet, but I'll come back to the ratio of consecutive terms and ratio of finite differences being constant. Well, the ratio of consecutive terms, we did see that explored a little bit here. Again, this is not a perfectly exponential system, but the ratio of consecutive terms was quite close to constant, and of course for an exponential function it would be. We'd be looking at 2 divided by 1, 4 divided by 2. Of course those are constant because that's how each number is obtained, is by multiplying each value by a constant common ratio. Okay. The graphical interpretation is that it rises to the right, as has been mentioned. It also approaches a horizontal asymptote to the left. So as it drops off, it never reaches the x-axis, but it approaches. Okay, now we could use the graph and calculator to look at finite differences. If we were to go back to our data and explore our data a little bit more here, we can go up to the L3 and we can perform finite differences on that, just to see if in fact there are any constant finite differences. So second list, operation number 7, and we can perform that on list 2. When we do that, an interesting thing happens is we actually get the exact same values, just offset by 1. So clearly here, repeating the finite differences again isn't going to give us a different result. It's just going to produce an identical set of values that are again just shifted offset by 1. So here we have another property of exponential growth or exponential relations. In addition to the ratio of consecutive terms and a ratio of finite differences being constant, it's also maybe worth mentioning that the finite differences themselves are never going to be constant. It's simply the ratio. Okay, and I'm looking at the data there. The ratio of finite differences would be exactly the same as if we took the ratio of y values, because in fact the differences in those are the y values themselves. Okay, so we could explore that with the relation y equals 2 to the x. If we were to take first differences here, we would get 1, 2, 4, 8. Second differences would be 1, 2, 4. And given enough y values, we would see that the finite differences always just reflect the y values themselves and would never change. Okay, so finite differences are not constant. The ratio of them are. Okay, so those are the main properties here for exponential growth. At this point, maybe just to wrap up, I just want to spend a little bit of time on some of the prerequisite skills. So as we get closer to looking at the exponent laws, we'll want to be able to work from what we know, which is the rules involving product of powers, quotient of powers, and a power of a power. So looking at some variable examples here. So the product law states, or product rule states, that when we have powers, sometimes it might have been written as a to the, or perhaps b, if we use base, b to the exponent m times another power b to the exponent m is equal to b to the exponent m plus n. And that's because when we're multiplying powers, each power represents repeated multiplication. So this is m factors of b. This here is n factors of b. And so collectively, if we multiply them together, then we're just going to be adding, taking a sum of the number of factors. When we divide, it's the opposite. The n factors of b take away from the m factors, which can do two things. It can decrease the number, and sometimes it can actually even make the number negative. So for example, 10 to the 3 divided by 10 to the 7 is a number less than 1. It's a negative exponent. It would be 10 to the negative 4, 3 subtract 7, and that would actually be equal to same as 1 over 10 to the 4, okay? Which we could see if we were to write 10 to the 7 as 10 cubed times 10 to the 4 using the product rule, and 10 to the 3, and then canceling across multiplication, leaving us with 1 over 10 to the 4, okay? So that actually highlights a couple things. It highlights the effect of the powers in a quotient, and it also brings out the negative exponent rule, which you may or may not have had a lot of practice with, so we'll review that as well. But for some of these examples here, we're looking at simply adding exponents when we see 2 or more powers of the same base. So this is the same base y, so we can add those and get 19. When we have quotients, we're subtracting, so this would be m to the 1. This would be h to the negative 2. This is a root, so that one there might be best left for a while until we can cover radicals and roots and exponents and the relationship between those. This is pretty straightforward. This is x to the 5 as we subtract here. Now, when we have a power of a power, taking something like this would be maybe best shown in fully expanded form. So this is y times z squared, y times z squared, y times z squared. So what we've actually done is we've cubed y and we've cubed z squared. So collectively we're going to get y times y times y, which is y squared, and we're going to get the cube of z squared. So clearly we can take the exponent 3 outside the brackets and apply it to all the parts of the product inside. So this is called power of a product, actually, and it would be in general form written something like this. We could take a, b to the m, and this will be written as the m power of a and the m power of b. Okay, so that is only when we have multiplication. That does not apply across addition or subtraction. So we never apply it like this. Okay. Simplifying this, then we would now get y cubed, and then this is your more familiar power of a power when we multiply exponents. So z to the 2 times 3, z to the 6. Okay, so this might bring back some of the properties that you've studied in grade 10. Further examples here, maybe I'll leave for you. Let's look at number 3. These are numerical examples, which are probably a little easier for you to relate to, and I would agree. So here, as long as the bases are common, we can add the exponents. 5, got 9. Here, keep in mind that the brackets is necessary because it separates the negative from the 1. But in this case, we want the power on -1. So that's repeated multiplication of -1. So this would be -1, bracket around it, to the exponent 11. That would be a negative number rather, because the exponent is odd. D, again, we'll come back to questions like that later on. E would be, again, -5 is the base. Keep that with brackets around it. 2 times 2 is 4, so this would be -5 to the 4. To evaluate that, we'd actually have to multiply -5 times itself 4 times, or apply the exponent. This would be power of a power, so 2 to the 15, 5 times 3, divided by 2 to the 14. And then we don't need to necessarily have it in a fraction form. We can just know that as a quotient, we subtract exponents. So we get 1, 15, subtract 14. In looking at the rest of the examples here, I'll leave those for you to practice. And let's just finish up with one more here. The zero exponent law. So this is going to be one that actually comes out of this Blackline Master, which you've received. So the prerequisite skills. One of the questions looks at the powers of 3. So this would be 27. 3 squared is 9. 3 to the 1 is 3. Now the pattern here seems to be that we're dividing by 3, or I'll write it as multiplying by a third. So if we continue to multiply by a third, we would find that if we multiply 3 by a third, we get 1. So actually that brings out one of the exponent laws, which is that for any base, non-zero base, when the exponent, which is x, exp, when the exponent is 0, the result of the power is 1. Now the question has us go a little further, and it says, what is the result if we extend this chart to include negative values? Well, if we were to do that, we'd actually discover the negative exponent law all over again. If we went to an exponent of -1, 1 times a third is a third. If we went to the exponent of -2, we get 1 over 9. -3, 1 over 27. And actually what we find here is that when the exponent is negative, we just get the same result as if the exponent was positive, except it's the reciprocal. This is 1 over 3 to the 1. This is, if I was to rewrite it, this is 3 to the -2, according to the function equation. This is 3 to the -3. And simplifying this is 1 over 3 to the +2. 1 over 3 to the +3. So a negative exponent just involves the reciprocal of the positive power. That's all. Okay, going back here to these questions, we have some where the exponent is 0. We don't need to really look at the base. The result is 1. Now, we'd also see that here. This would be 6 to the -1 times 1, or we could just add the exponents. -1 times, or +0 is -1, so no change there. Now with positive exponents, that would be applying that negative exponent rule, which would be like this. B to the -m would be the reciprocal of b to the +m. So keep in mind, the base does not change. The exponent is made positive and you take the reciprocal. So 6 doesn't become -6, stays as positive 6. Some of these here are a little tricky. We've got to be careful. The difference between negative 4 to the 0, which is 1, compare that to negative 4 to the 0, is that exponents in BEDMAS take priority over multiplication. And this is more appropriately written negative 1 times 4 to the 0. Here's the power, here's the factor. So we would have to first do the power, which is, as a result, 1, and then multiply. Okay, so you can see the difference in the outcome with the brackets versus no brackets. Okay, maybe just one more here for practice. We're looking at, say, 4 to the negative 5 times 4 squared would be 4 to the negative 5 plus 2, which is 4 to the negative 3, which is the reciprocal of 4 to the positive 3. And it says to simplify express answers with positive exponents, which we've done. If we were to actually evaluate that, it would be 1 over 64. Okay, so there's a good review of some of the basic exponent laws you'll probably find in the back of the textbook if you were to go to your prerequisite skills section. You'd find that in the appendix, I would say exponent rules are on page 483, so if you're having a hard time following some of this, that's a sign that you need to look at some extra review. And I would say as you go through the week and this chapter, make sure that you complete a majority of these questions. At this point, the ones I think you should be able to attempt are certainly 2 and 3. Having looked at 4 already, I would say try to do as much as possible of 5 as well. And when you get into some of the expressions in number 6, you may struggle with that a little bit because they're variable powers. 7 is just a review of domain, range, and intercepts. We've covered that a lot this semester, so that's just making sure you are familiar with those. And so I'd say probably for the most part we could, at this point, ignore 7, 8, and 9. I believe at this point we've probably not covered transformations, so we'll leave that until we look at all the different relations as a set. And work for this section at this point, I think we've probably already done in class on day 1, the investigation, the simulation, and you've taken the note now, so coming in tomorrow we'll be looking at warm-up and group work with those following questions. I'll see you then.